infrared. Because we are specifically, they have specifically looked into infrared spectra of alcohols and phenols. So the requirement is a bit more than just knowing the OH peak, strong and broad, and sp2 and sp3ch. Okay, and also the requirement includes, the alcohols and the phenols also have the CO bond, and the CO bond is not in the standard characteristic group region. Okay, is somewhat you can consider fingerprint region. Okay? But the CO stretching itself is, pretty visible because of the CO bond also is a pretty polar bond, so it's usually pretty intense. May not be as intense as a carbonyl, but still pretty intense peak. And also the frequency reflects the, the hybridization state of carbon. An sp3 CO bond in what you can see in regular alcohols, generally its stretching frequency is about 1050. Okay? And if you have F or 1100, but if you have sp2 CO bond, that's the one you see phenol. Okay, it's about 1200, reciprocal centimeter. So that's something you need to look for. Say if you say, oh, the which one is cyclohexanol? Okay, so then the obviously you can exclude those spectra that do not have intense and strong OH peak. So either will be first one is cyclohexanol, okay, or the last one is cyclohexanol, because those two, they have intense OH peak. So those are the two ones, okay. But which one is cyclohexanol is that, you basically, you need cyclohexanol, you have sp3ch, and you don't have any sp2ch, and the CO bond should be around 1100 reciprocal centimeter. So that, this is sp3ch, you can see a little below 3000. Okay? You don't have any sp2ch here. And the CO bond, indeed, you have a somewhat below 1100, 1080, maybe 1080, 1070, okay, reciprocal centimeter. So this should be a cyclohexanol. Okay. And the other one, you guess, can some of you can give me some idea what might be? You see the intense OH, have OH, no question, okay? And the sp3ch, you don't see much, okay? And you might have some sp2ch, okay, here, but it's hard to say, okay? Because of its on top of very intense OH peak, so you might have difficult to directly see it. That's just real world, if you really see infrastructure, not everything ideal to let you see all the peaks. Okay? If a weak peak is overlap with very intense peak, you might have difficulty to resolve it. Okay, but the key part is if you look at CO stretching, you don't see anything between 1000 and 1100, but you do see an intense peak, slightly above 1200. Okay, so this supposed to be something with sp2 CO bond. Okay. So if phenol is one of the options, then this one should be phenol. Okay? Because phenol is the one has the sp2CO and also has OH bond. So that is, how do you approach this kind of question? But see, if your compound has OH group, so those middle three ones certainly cannot be. Okay, absolutely cannot be because they don't have OH. You don't have intense and a broad OH peak. Okay. Now, proton and NMR, cyclohexanol. Okay, so the cyclohexanol, well, first, if you do have a cyclohexanol, how many kind of protons you might have? Cyclohexanol. Good. Okay. Cyclohexanol. This, okay. How many kind of protons you can have? One kind of, right? Then it does, you know, but to be honest, this guy's cyclohexanol may be a slightly more complicated because you have this supposing into this chair conformation. Chair. How do I draw a chair? Okay. So you basically you could have you know anyway, but at least you're gonna have like a 3-4 types of protons. Yes.
You can see 4 different readings, right?
Well, if we don't consider chair conformal, okay. You know, but in most of case you can't, you know, because of at the normal temperature, the two chair conform, you know, they are flipping between two chair conformals, so the probably don't need to worry about it. So yeah, that's basically, you see the, you know, it has a, you can consider this molecule has a twofold symmetry, mirror plane, cut the molecule into halves. Okay, so yeah, you can have 4 kind of protons. Okay, so it can't be this one. Okay, you know it certainly cannot be this one because of the, you know, you have a bunch of aromatic protons here. Okay, and the also it cannot be this one. Okay, so only possibility is this one. There's no other possibilities. Okay, no other possibilities. Okay? Although this one is hard to say how many protons you see because depending on your resolution, technically you could afford, you have 4 different kind of protons, but because of proton and the mass spectroscopy, its resolution could be limited because you only have 10 ppm range. So technically you may have trouble to resolve all of them. Okay, so but only this one can fit. Okay? Because this one single proton obviously doesn't work, right? And then this one 10 protons, only 2 types, also won't work because at least you have OH proton somewhere. Okay, so then only this one can be right. Okay? And then the last one, carbon-13 and NMR, is basically just, you know, if it's phenol, phenol obviously can cut it into mirror imaging 2 halves. So you should have 1, 2, 3, 4 type of carbons. And their chemical shift value should be all around 120 ppm, and with this guy a bit higher. Okay, so that's something you can look at. Which one looks like to be the right one? Yeah, only the second one, because of all of them are aromatic. Okay, an aromatic one, it's you know most of aromatic around 120. The carbon direct bond to O will be highly deshielded 150 something. That's how you figure out the, you know, those 3 spectroscopic problems. Okay. Do we have any spectroscopic problems? No. Nine? What is this? Oh, most acidic one. first, you don't need to memorize anything here. So the phenols, they are much more acidic than regular alcohols because the oxygen lone pair can be, the partially delocalized into the ring. Okay, so that makes the this OH bond, or maybe simpler if you look at their conjugated bases, acidity of those acids, they are directly related with the basicity of their conjugated bases. So you find out that all the conjugate bases of those four compounds, and then the in phenoxide, the negative charge, all phenoxides, the negative charge of the oxygen can actually delocalize into ring. So that makes all phenoxide, each and every one of them, more less basic than the alkoxide. Each of so that means all phenols, each one of them will be more acidic than cyclohexanol, because in cyclohexanol there's no mechanism can let this oxygen lone pair to be delocalized. No mechanism. Okay, so in the conjugated base of cyclohexanol, the alkoxide, the negative charge is fully localized. Okay, fully localized. Okay, onto the oxygen, fully localized. So this is the most basic one. So this guy, okay, is the least acidic one. So all the phenols are more acidic than cyclohexanol. Now, among three phenols, both these two will be more acidic than this one, both of them, because of nitro group is the most powerful electron withdrawing group. So the attachment of nitro group doesn't matter where they attach to the ring, will enhance acidity. Okay. Now the question is which of those two is the more acidic one? You have to look at their conjugate bases and carefully inspect how well the oxygen lone pair can delocalize. So if you look at the also version, and the meta version. Basically, you're going to look at conjugated base. Okay. So you need to use resonance if you draw the resonance forms to, of course, if you did your work, as I asked you I did ask you to draw the meta form last class. I did ask you whom to draw. If you did that, you will see that in the meta, the form, this guy, there's no way to place the negative charge of this oxygen into the nitro group. There's no way, okay? But in the ortho form, there's a way to place the negative charge all the way into the nitro group, okay? So because of the existence of the resonance form, I'm drawing now. So when the nitro group either at ortho or para to the oxygen atom, the oxygen lone pair can actually fully delocalize into the nitro group. And this give you one of the most stable resonance form other than this guy, okay? So that, basically illustrate that negative charge can more effectively delocalize in the ortho version or para version of the nitro phenoxide. Okay? But this mechanism, this pathway is not available for the meta version, only available for the ortho and the para version. So if in ortho or para version, the negative charge can be more effectively or more efficiently delocalized, that will make the ortho or para version of the phenoxide more stable, less basic. If the base is less basic, means the conjugate acid will be more acidic. So this means that you can create a ranking. This is a most acidic one, okay? This is second most acidic one. And this is third most acidic one. Then you can answer the question. Okay? Huh? Just conventional phenol. Because of the even in conventional phenol, the oxygen, the lone pair from the oxygen atom can be somewhat delocalized onto the ring, but such a mechanism does not exist for the alkoxide, regular alkoxide, because this carbon is sp2 hybridized, cannot accept the lone pair go into it. No, I already told you the total ranking, so you can answer the different variety of the question, I'm sure. Yeah. Apart from.
Yeah.
Okay, Roman number. Reagents for each of the two operations. Okay, so what you can see is to analyze this reaction. Okay, you are losing a carbon, right? From here to here, you're losing a carbon. Here you have 7 carbon. Here you have 6 carbon. Okay? So you have to cut a carbon-carbon bond. And the only reaction that cut a carbon-carbon bond in the 3 chapters we have learned. Only one reaction. What's the reaction? Cut a carbon-carbon bond. Usually we are doing synthesis, right? Either do functional transformation, but here you're losing a carbon. We only learn one reaction in that 3 chapters. Check what reaction? We can cut a carbon. Only learn one reaction. We can cut carbon bond. What reaction, right? Only one reaction. Chapter 16, look for it. Okay? Only one reaction. We cut carbon bond. That reaction very similar to a reaction we learned in chapter 8, organic 1. There's one reaction. Very similar, yeah? Yeah, very similar with ozonolysis. But it's not, ozonolysis is not something we learned in chapter 6. It's very similar with ozonolysis. That's correct. Yeah, periodic acid reaction, periodic acid cleavage. Okay, so because just look at the. So you see a problem, just look at the whether the functional group transformation or you need to add something. Obviously, not add something. You cut something off. Then you have to. That's only one reaction. Proxy acid, periodic acid, or whatever. Periodic acid, we call it. Okay. So just knowing that, we just treat it with HiO4. So but this reaction is not a single step. So you cut it off, you have to do some conversions. So this one, just like ozonolysis, you cut this one off, and the CO cut the carbon-carbon bond, and the CO single bond becomes CO double bond. That's simple. Okay. So this will the left side of compound become this, and the right side of compound become this. Okay, but it doesn't really matter. We don't care about the second compound. What we obviously care is what we're gonna do with first compound, right? But first compound is not the target compound yet. How do we convert this one to the target compound? Can anyone tell me? How do we convert a cyclohexanol into the target compound? This is what kind of if Okay, yeah, we're gonna reduce because of functional group transformation. You need to transfer the CO double bond into CO single bond. Okay, that's a reduction reaction. So a number of ways you can do it. Okay, a number of ways you can do it. Huh? Chromium 6 is a believe oxidation agent or reduction agent. Yeah, you need something with a low oxygen state to do the job. Okay, so hydrogen is good. Hydrogenation. Yeah, or in a laboratory setting, we often prefer sodium boron hydride because hydrogen is kind of dangerous. If you mishandle it, it's easy to cause explosion. If you mishandle it, if you're very careful, follow the safety protocol, you will not, nothing will be happening. But if someone, doesn't care about too much about safety rules, then it could have been a bound to deal with. So in a number of ways. In a laboratory setting, we actually prefer this. You can do sodium boron hydride in water. Okay, that would be even better. But you could use catalytic hydrogenation. Lithium, yeah, you can use that, but that requires more strict environmental controls. Okay, so you have to avoid moisture kind of things. Yeah, but if the sodium boron hydride works, we don't want to use the lithium boron hydride because let's say again, if someone is not so careful, spill some water into it, can catch fire. Okay, so sodium boron hydride is milder thing to work on. And the second transformation, if you look at it, okay, it's a functional group transformation. Basically, you convert. You're not losing carbon. You're not adding carbons. You convert a regular alcohol, okay, into a bisphenol diol. That's your conversion, right? Rest of them are the same. Okay? You're converting a regular alcohol to bisphenol diol. That's how you're gonna, approach this problem. You analyze you don't have the same number of carbons. Only difference is you convert a regular alcohol to bisphenol diol. And obviously, we didn't learn a single method that can do it in a single step. And we only learned a single method can make a bisphenol diol in chapter 6. Only one method, bisphenol diol. What is the method in chapter 16? Yes, osmium tetroxide, mediated oxidation reaction. Okay? So if there's only one reaction, then it's straightforward. Just say, okay, before you can get this one means you will need this one. That's the retrosynthetic analysis. Why this thing always come up? I hate that. Let's just copy this. I use the most powerful image processor app. I'm just kidding. It's the simplest image processing app. Can I paste here? Okay. Okay. So basically, you do the one-step retrosynthetic analysis. You will need this one. Basically, if you want this, actually, I want to correct, okay? So if you want this Wissner diol because of cyclohexene is no longer have the chair conformation, okay? So basically, just this one will be sufficient. Cyclohexene derivative, you have chair conformation, but cyclohexene is not, okay? So that's your, that means if you do one-step retrosynthetic analysis, you will need this one to get the product, right? You will need this one to get the product, okay? And the starting material is, I can erase the image, okay? But you just with a single OH, let's say, can I just cover it? Shape. I can't cover it, okay? But anyway, assume that the starting material is just this guy. Starting material is this one, right? That's starting material, okay? So can you use a one-step retro? Can you think about one step I can converting the black compound to the red compound? Yeah, sulfuric acid. What do we learn organic one? Acid catalyze the dehydration. Now we complete retrosynthetic analysis. Just write out all the forward reactions. So you will need that compound. The heat with sulfuric acid. And by the way, I want to make a comment on some of your homework because I already graded some of your chapter 15 homework. I have seen that many of you, I mean, actually only like 4 students submitted. So out of 4 students, at least like 2 or 3 of them, when you're doing the synthesis of alcohol using Grignard reagent, let's say if you have this Grignard react with this ketone, okay? Many of you wrote as a THF acid, okay? Then give me the product, okay? If you show me this answer, okay, in the exam you will be wrong, okay? Why it's wrong? What's wrong here? What's wrong here? What is wrong here? Huh? What is wrong here? Basically, look at it. The key part is this is wrong. Okay, this is wrong. Okay, why? You are implying that you are mixing these two things at THF S at the same time. You have to say one of the two. Because why you draw the reaction arrow like the one showing here, imply that they are placed together. Or the sequence doesn't matter at least. You can add whatever, which doesn't really matter. That's not, of course, not true. You have to add a THF that the mix after that complete that added acid. You have to write 1 and 2. Yeah, diester is a THF. That doesn't matter. That only have minor differences. Diester has a lower boiling point. THF has higher boiling point, and generally THF is better unless you specifically want your reaction happen at a lower temperature, so that you can use the boiling of diester ether to as a temperature control manual. Okay. But usually THF. Yeah, I don't care. For example, I don't care. Well, for most of practical purposes, they are the same. So that's I noticed many of you. Okay, if you lose point from that, it's it can be easily avoided. Okay, but anyway, for this question is basically you start from after we complete ritual synthetic analysis. You said you got alcohol starting material, treat with sulfuric acid, then treat with OS, O4, and a few other things. You need organic peroxide. Peroxide, okay, this is real oxidation agent, and let's say you can have a tertiary butanol, then need a base to complete the reaction. So that is the what? Well, those things different. Those things they must be used at the same time. So that's the standard. Okay? Because the osmium tetroxide is a catalyst, so it must be used together with the organic peroxide. That's the real oxidation agent. And then the tertiary butanol is commonly used as solvent, or you also need a base to finish the job. So all those things must be added together. Yes? 12. 12? 12. 12. 12. Oh, 12 is the first part you're talking about.
No. That one.
Oh, okay. So basically, for this kind of thing, there's many possible. At least there's 3 types of possible answers. So you can randomly cut one of the So this carbon, okay, has to be from carbonyl carbon. That is clear, okay. The essential carbon must be from carbonyl carbon, and then remaining 3 groups, one of them will be from the organolithium, right? Did I say organolithium? I can see. Oh, organolithium, yeah. One of them could be from organolithium, and the rest 2 are the groups on the carbonyl group. But there's 3 possible answers. So we could potentially cut off here, okay? So then treat the left side as from organolithium, okay? And then the right side 2 substituents, okay? And the central carbon as they are from carbonyl. So this is one possible answer. One possible answer, okay? But not the only one. But certainly you also, it's nothing wrong to, I don't like this. I just draw here. Okay. It's easier to do the. Okay. So that was one answer, but you could have. So the central carbon, this one, has to be from carbonyl. Okay. But you could have other possibility as well. So let's say you could cut this one. Okay. The bottom one as from organolithium. So you're going to have methyl lithium, okay? And then the remaining two from carbonyl. So you can have this one, carbonyl. This also could be the right answer. This combination also could be right answer, okay? But also it's not wrong if say, okay, I prefer to consider the right side ethyl group from organolithium. Now, if you take that one, you say ethyl group is from organolithium, then those things gonna be from the carbonyl compound. So you're gonna have a cyclohexyl group. And this combination. All the combination will be fine. Any of them gonna be correct. Okay. Any other questions you would like to ask? If not, then we're gonna Question 5. 5. Which part? Someone.
Page 1.
Well, so first look at this conversion. Okay, is what kind of process? It's a reduction process. Okay, and the key part is you have a reduction process, also the addition process. So you need the solvent reagent combination to selectively undergo addition to the carbonyl group, but not the CC double bond. And it has to be single step reaction. It's a reduction process. And you don't want to reduce the CC double bond. So what should be avoided? If we, yeah, you don't want to use H2 because H2 gonna reduce both, not selective. Okay. So what's available to you? If not H2, what else can reduce carbonyl group to alcohol? What else can do the reduction job? Yes. Yeah, NaBH4 may work, and the lithium aluminum hydride may work. Okay, but I also said a single step reaction. Lithium aluminum hydride always is doing 2 steps because you have to add lithium aluminum hydride diether or THF first. After finish, adding water, acid, whatever. Okay, so you have to use sodium boron hydride. Okay, sodium boron hydride that's an advantage of sodium boron hydride. It can work with water or alcohol. Okay, and it can selectively reduce carbonyl group. Yeah, sodium boron hydride. That's the good one. Yeah, but just observe it, analyze, then retrieve from your memory library, the answer. Okay, I'll see you guys next Monday. As usual, I'm gonna post the answer keys 4 p.m. Sunday. And if you need more time, come 7:45.